Okay, welcome back. So this is our study, and so I want to show you what a table might look like, at least what my tables look like from studies where we develop models. And for me, it's extremely important to present the models along with the coefficients so that people who read the paper and have the interest can take the coefficients and compute the probability of mortality for their patients. And from our model, from this is the NPM0. This is the model that estimates the probability of mortality based on data available at the time of admission to the ICU. And there were 12,610 patients who were in this developmental data set. And you can see the coefficients, and I always present the coefficients, the standard errors of the coefficients, but I understand that readers, especially in medical journals, don't really understand what beta is. They don't. If you tell them it's the log odds ratio, that doesn't really help. So I always present a column of the odds ratios. Now again, I hope that helps, except people don't really interpret that correctly because they think they're talking about relative risk. But odds ratio is, I always present the odds ratio because at least it has a sense of something about the severity of these particular conditions. And then I present a 95% confidence interval for the odds ratio. I always will present my tables in that way. Notice I've taken my variables here and I grouped them by the type of variables. So I have my physiology variables grouped, and then I have my chronic diagnoses variables grouped, and then acute, and then other. So there are a number of things to point out here about this table. I mean, one is that I do give all the coefficients so that anybody who encounters a patient and knows these coefficients can compute the probability that this patient will die in the hospital. And so the interpretation of this is that, looking at the odds ratio, we all know that this tells us that a patient who's in coma or deep stupor at the time of admission to the ICU has odds 4.42 higher odds of dying than a patient not in coma or deep stupor, controlling for all of the other variables in the model simultaneously. And you can say that for each of the variables in this model, and all of these variables are highly significant. Okay? Now, the way you get the odds ratio, as you know, is you take e to the coefficient. E to the 1.485 is 4.42. But when it came to the continuous variable age, and assuming linearity in the logit, which we looked at and decided, okay, we do have linearity in the logit, we didn't just take e to the coefficient, we took e to the 10 times the coefficient. And so this 1.36 is the odds ratio associated with 10 additional years of age. So someone who's 10 years older than someone else, their odds is 36% higher of dying than the younger person. Okay, now I hope that's clear. I chose the 10 years. I could have chosen 5 years, I could have chosen 20 years. I chose 10 years. And because of that, because I didn't simply take e to the coefficient, I broke out the 10-year odds ratio in a different line so that my reader would know what I use as the multiplier. Okay? All the others are simply e to the coefficient, but not that one. So this is the model. And then here's the goodness of fit test for the model. And so we have the model, we have then, here's my 10 groups, observed and expected in each group. Again, if you do a quick look at these observed numbers and expected numbers from cell to cell, you'll see that there's pretty good agreement. And the p-value is 0.623 with 8 degrees of freedom, suggesting that we have a very well-calibrated model where we're estimating the probability that the patient will die who enters the intensive care. Here is here's the same goodness of fit test, except we're using 0 to 10%, 10 to 20%, so the probabilities are pre-grouped. And what you can see here is that, again, I have observed and expected counts. You see that by the time you get to 90 to 100% probability of dying, I mean, most of those patients die, to be sure. Okay, but the numbers are getting more thin, but we're still not in any kind of problem, and we have plenty of numbers. We have a very large sample size here. And when we look at the goodness of fit test here, we call this H. We got a p-value of 0.57, and again, it's indicating that the model fits. And the area under the ROC curve is 83.7%. And so, again, suggesting that not only do you have good calibration for this model, but you have good discrimination as well. Now, here's the validation data set. So remember, I set aside some portion of the patients, and then we want to see whether the model fits for those patients. And here we have those. There were 6,500 patients in the validation data set. Again, if I could do this over again, I'd probably have less than 1,000 patients in the validation data set, and I would have all the others going into developing the coefficients. But anyway, this is what I have. And again, you can see that comparing the observed and expected counts from cell to cell is pretty good agreement. The p-value is 0.327, and the degrees of freedom is now 10, not 8, because I did not develop the model on any of these 6,514 patients. This is an independent group that I'm evaluating the model on. So we can see that you have good discrimination, good calibration in this group, and good discrimination because we have 82.4% is the area under the ROC curve. So, you know, back in the old days, once you had a model, you had to teach people how to use the model. There weren't, you know, nice solutions like web pages that people could simply go online, get the web page, put in the values, pull down menus, everything to compute the probability. So to show people how to use this, I considered here as, I would take a scenario. And so this is a 60-year-old man with alcohol-induced cirrhosis. And notice I'm color-coding keywords because the keywords are part of the model. Is an emergency admission to an ICU. He suffered a significant GI bleed that resulted in a drop in his systolic blood pressure to below 90 millimeters of mercury. At the time of ICU admission, his heart rate was 130 beats per minute. So somebody collects these data, and then we go through the list. This is the model that I showed you. Go through the list and say, okay, was the patient in coma or deep stupor? No, but yes, the patient's blood pressure was less than 90. Yes, the patient had cirrhosis. Yes, the patient had a GI bleed. The patient was not for, admission was not for elective surgery, and the patient was 60 years of age. So you know what you have. Then there's a spreadsheet somewhere. And in this spreadsheet, we have the coefficients buried in column 500, so nobody has to see them. And then you simply plug in the values of x, and the spreadsheet computes x times beta. So here's beta naught plus beta 1 times x1 plus beta 2 times x2. At the end of the day, you have the logit. And then you take e to the logit over 1 plus e to the logit, and you get 0.54. And okay, so here's a patient whose probability of dying is 54%. Okay. And so that's, again, that's good for the medical staff to know that this patient is more likely to die than to not die. However, understanding the meaning of probability is not that much more than 50%, and it's only indicating that 54 out of 100 patients with this probability are expected to die by the model, but 46 out of 100 are expected to live. So how you use that, you know, obviously should be taken into consideration. Okay, so by the way, this model that I showed you, this model that we published, has been tried in many countries as using the country data as validation data. And you find that these models, especially older ones, don't necessarily work in modern ICUs. Technology changes, things change. So there are a number of things that people can do. I mean, one thing is, instead of going through a whole model building exercise, they can take our variables and refit the coefficients. I mean, that's one strategy. The other thing that people can do is they could compute the logit based on these coefficients, and then simply take the logit and use that as the only independent variable in a new logistic regression model, and then see how the fit is using our logit, but with a new weight, a new beta weight. So there's different things that can be done, and so people will present the results of their refitting of our models in their countries, in their ICUs. Okay, I think we'll take a quick break. And then I want to come back and show you my world's most famous slide, not famous slide, my favorite slide in the world last.